Welcome back. In this session, we will map object-oriented concepts that we studied in C++. Here's how we will proceed. First, we will define and recall the classes and objects concept. We will explain constructors and the role of self keyword. Then we will switch to operator overloading and cover concepts like inheritance and polymorphism. We will compare C++ and Python OOP paradigms side by side. So throughout I will show you equivalent C++ examples so you can map between C++ and Python easily. So let's quickly recall what a class is. So a class is simply a blueprint. It describes what data an object will hold and what operations it can do. An object or an instance is basically a concrete variable that follows that blueprint. In Python, class definitions are very lightweight. You define them with the class keyword and add attributes and methods inside. No need for header files or access specifiers are by convention. We will see how. And objects are created at runtime. So here's a simple dog class. Species is a class attribute shared by all instances. The init method is the constructor that runs when you create a new object. Inside methods, we use self keyword to access the specific instance attributes. When we create an object of dog class like d is equals to dog of rex, 3, so initializer or init method stores the name and age on that instance. Calling d.speak runs an instance method that accesses self.name. So that _init and ending with again double underscores is basically an initializer. Self keyword is the reference to the current instance of the class with the same role as you can recall of this pointer in C++. You always write it explicitly in Python method signatures. Remember that self is just a parameter name by convention, but it is strongly recommended to use self everywhere for better readability. Let's talk about encapsulation, that is the concept of controlling access to the internal data and methods. In C++, the compiler enforces this through explicit keywords like public, protected, and private. In Python, there is no compiler level enforcement. Instead, Python relies on developer conventions and a simple name mangling mechanisms. Every attribute in Python is public by default. You can read or modify it directly. The philosophy is we are all responsible adults, so Python trusts the programmer, so there is no need to write public as in C++. A single underscore, that is underscore data, signals protected intent. It is a hint that this is for internal or subclass use only. The interpreter doesn't stop you from using it, but other developers understand that they shouldn't access it directly. So this is Python's agreement style of encapsulation. So you can see in this example of class name sample. So the attribute value is public by default. So it is accessible as you can see we can create an object and access it in a print function. So for protected convention, you can see a class hierarchy with the base class and a derived class from the base that inherits from the base class. So with one leading underscore, we can signify the protected convention. So you can see with one underscore the data attribute, the attribute name data. So this signals basically the protected convention. So that is how you can create an object of a derived class and then access that attribute using that object. So as I just explained, that an interpreter doesn't stop you from using it, so you can call it in a print function, but you shouldn't do this. Python emphasizes readability and flexibility. It avoids strict barriers that might hinder debugging or quick exploration. So protected attributes exist by convention rather than enforcement. When you prefix an attribute with 2 underscores, Python performs name mangling. The variable's real internal name becomes underscore class name underscore variable name. That is why direct access, that is s dot double underscore pin, fails. because the name literally doesn't exist. But if you really want, you can still reach it using underscore class name and then double underscore variable name. So this is not true privacy. It is a safeguard to avoid accidental name collisions, especially in inheritance hierarchies. Now let's look at how Python handles private data inside a class. When you write a variable with two leading underscores, like you can see double underscore pin, Python performs something called name mangling. That means it internally changes the variable's name to include the class name in front. So inside the interpreter, double underscore pin actually becomes underscore secret double underscore pin. This prevents outside code from accidentally accessing or overriding the variable. Let's see what happens when we run this example. So inside the class, the line self dot double underscore pin works perfectly because Python automatically knows the mangled name. But if we try to access s dot double underscore pin from the outside, Python says attribute error. This object has no attribute named underscore double underscore pin. However, if we really want to, we can still reach it using the internal name, that is underscore secret and double underscore pin. This shows that private variables in Python are not truly hidden. They are just renamed for safety. It's meant as a discouragement, not a lock. In C++, the compiler blocks you from touching private data, but in Python, it is a gentle reminder that a variable is for internal use only. Now that we have understood encapsulation, let's talk about methods and the self keyword. In Python, any function that belongs to a class is called a method. When you call a method using an object like s1.display, the Python automatically passes the object itself as a first argument to that method. That's why every instance method in Python must have a self as its first parameter. The name self is not a keyword, it's just a convention, but it must be present in that position. Inside the method, you can use self to refer to that specific object's data. For example, you can see in this example, self.name and self.marks means the name and marks that belong to this particular student. This is very similar to this pointer in C++, which also refers to the current object, but unlike C++, where this is implicit, in Python you must explicitly include the self in your parameter list. Here you can see a quick comparison between Python and C++ with respect to current object, method definition, method call, and purpose. Now that we understand how classes and objects work, let's move on to one of the most important distinctions in Python's object-oriented model, that is basically the difference between instance variables and class variables. In Python, variables that belong to a class can exist at two levels, either at the object level or at the class level. Instance variable belongs to a specific object. It is created inside the initializer, that is the constructor, the init method, and each object keeps its own copy. Class variable, on the other hand, is defined directly inside the class body, outside of any methods. There is only one copy of it, shared by all the instances of that class. So if you change a class variable, the change is visible to every object. But if you change an instance variable, it affects only that particular object. Here is a simple class named student. It has one class variable, that is school underscore name, and two instance variables, name and grade. When we create two objects, s1 and s2, each one gets its own name and grade, but both share the same school name, that is school underscore name. Now watch what happens when we change s1.grade value. Only ls grade changes, but when we modify the class variable school underscore name through the class name, it instantly changes for all the students. So as you can see that after modifying ls grade, Bob's grade remains the same because each object maintains its own instance variables. But once we change the class variable, both students now show the updated school name. This clearly demonstrates that class variables are shared while instance variables are unique to each object. Here is a quick comparison between instance variables and class variables with respect to some features for instance variable belongs to basically a specific objects, and class variable belongs to the class itself, so it is shared. Instance variables are created inside using the constructor or initializer, and class variables are created directly inside the class body. With respect to storage, for instance variable, each object has its own copy, whereas for class variable, one copy is shared by all the instances. Instance variable is accessed with the help of keyword self.variable, and class variable is accessed using a convention that says class name dot variable name or cls dot variable. So if you try to map this to the knowledge that you gained in C++, you can say that instance variables relates to the normal member variable, and class variable is like a static data member, that concept that we covered in C++. Now here's something many beginners get wrong. If we try to change a class variable through an object, so here's an example class named test, and it has one attribute named x and it has value as 10. So this is class variable. Next we'll create two objects, t1 and t2. Now if we try to change a class variable through an object, like we have written t1.x is equals to 20. So Python doesn't actually modify the class variable. Instead, it silently creates a new instance variable named x for that specific object. This means that other objects and the class itself still hold the original value. To change the shared variable, always use the class name, that is test.x is equals to 20. So here's a correct way of doing this. So to properly modify a class variable, always refer to it using the class name, not through an object. So when you write test.x is equals to 20, you are explicitly telling Python to update the shared variable that belongs to the class itself. Now all instances, both old and new, will see the updated value. So in Python, methods inside a class can be of three main types: instance, class, or static methods. Each type behaves differently depending on what data it works with and how it is called. So here's an example class named student. It has a class variable named school_name, and then we define an initializer that initializes the instance variables named name and marks. Now we have written three methods. One is instance, class, the other is class, and thirdly the static method. So let's start with instance methods. It refers to the attributes using the self keyword, that is we write self.name and so on. So when we call s1.show, Python automatically passes the object s1 as a first argument to self. Next we have class methods, which uses add class method decorator. A class method receives the class itself as a first argument and conventionally named CLS. It doesn't deal with individual objects data. Instead, it is meant to access or modify class level attributes or variables that are shared by all the objects. In this example, change_school changes the value of shared variable. So if we run student.change_school and pass xyz school as a parameter to it, every existing and future student object will reflect the updated school name. Finally, we have static methods declared with add static method decorator. These methods do not automatically receive either self or CLS. They behave like plain functions that just happen to live inside a class. They belong to the class logically, not by data access. So they are used for general purpose utility work that is related to the class. For instance, is_pass is a function that checks if the marks are greater than or equal to 40. It doesn't depend only on class or object data, that is why it is static. So in summary, instance methods knows everything about one object. Class methods know about the class as a whole. Static method doesn't know about both, but they belong to the class conceptually. So this separation helps us design cleaner and modular and more readable class architectures. So this is a comparative view of three of the methods that we just covered: the instance, class, and static method. In instance method, there is no decorator. But for class method and static method, they have their separate decorators. As a first parameter, for instance method we write self, for class methods we write cls, and for static method we write nothing. Next column highlights the access with the help of instance variable or class variable, and then instance methods are bound to object, class methods are bound to class, and static methods are not bound to anything. So if we can create or map to C++, instance methods are like regular member function, class methods are like static member function that we studied in C++, and static method means utility function, that is, you can say, a static scope. Now we are going to explore how common object-oriented programming concepts in C++ translate into Python. So we will cover operator overloading, inheritance, polymorphism, and the super function. Operator overloading lets you define how operators like plus or minus behave with your objects. Python uses special methods such as add method with starting and ending with double underscore for addition, and sub method for subtraction. So you can see in this class we have a class named point, and it has an initializer that sets the attributes named x and y to equivalent values. Then we define a special method named again add. That method is basically a special method for the add operation. So it returns the summed versions of 2 points, that is, it adds 2 points together. Now you can create two objects of point class, and then finally you will write p3 is equals to p1 plus p2. That line basically calls the special method that we have just written named add. So we can define our own magic methods to implement operator overloading in Python. So magic methods in Python are the special methods which add magic to your class. So they are not meant to be invoked directly by you, but the invocation happens internally from the class on a certain action. For example, when you add two numbers using the plus operator, internally the add methods with the preceding and ending double underscores method will be called. So here's in a category with respect to some operators like binary operators, then we have extended assignments, unary operators, and comparison operators. So operator overloading in Python lets you define custom behavior for operators. Let's look at examples of each category of magic methods. So binary operators, here we define a point class. By implementing add, we can add 2 point objects using plus. This is similar to overloading operator plus that we covered in C++. Next, for extended assignment, that is iadd function. So the counter class shows plus equals to using the iadd. Instead of creating a new object, the existing object is updated in place. Unary operators like negation can also be customized. In the vector class, neg name function flips the signs of x and y. So minus v or negation of v produces a new negated vector. As you can see, 2 becomes minus 2 and 3 becomes minus 3. Finally, comparison operator. So comparison operators like less than are overloaded using the methods such as that again underscores, and the name is lt. Here box objects are compared by their volume. So as the volume of b1 is less than b2, though that is true, so we can see true in output. By using these magic methods, Python lets you make your objects behave like built-in types. So this is one of the most powerful features for writing intuitive and clean object-oriented code. We will understand one of the most powerful object-oriented features, that is inheritance. It allows us to create new classes based on existing ones, and this promotes reusability and scalability to our code. So inheritance means one class can inherit attributes and behaviors from another. In Python, we can define a derived class by placing the base class name in parentheses. For example, you can write dog and in parentheses you can pass animal, and that means dog inherits from the class name animal. There are several types of inheritance like single, multiple, multi-level inheritance, and we will see each with examples. So we define a base class animal with the method eat. Then we create a drive class dog that inherits from animal. The dog class adds a new method bark. When we create a dog object, it can call both eat and bark. That is inheritance in action. That is, you use, reuse, or extend the behavior. Now let's go through the method overriding example. Here both animal and dog have a method named sound. So the dog class redefines it. So this is method overriding. When we call d.sound, Python runs the overridden version from the dog instead of the animal. And overriding lets subclasses provide specialized behavior while keeping a common interface. In a multi-level inheritance, a class is derived from another derived class. So in this example, you can see three classes. So puppy inherits from dog, which in turn inherits from animal. So puppy gets all three behaviors: eat, bark, play. This creates hierarchy that is perfect for representing real-world relationships. Python supports multiple inheritance. A class can inherit from more than one parent. Child inherits from both father and mother. If both parents define a method with the same name, Python follows the method resolution order, that is, father comes first. So c.skill calls the version from father. Next, the super function lets us call methods from the parent class. Here, when dog is initialized, super function basically first calls animal's constructor, then it executes its own logic. So super helps us avoid redundant code and ensures parent behavior is properly inherited. To summarize, inheritance in Python lets us build hierarchies, reuse code, and extend your functionality. So understanding it is a key to master object-oriented programming design in Python. We will explore polymorphism, that is one of the pillars in OOP, and see how Python's super method helps us manage class relationships neatly when inheritance is involved. So polymorphism literally means many forms. It lets you use a common interface, say a speak method, that behaves differently for different objects, for dog and cat. So in C++, this is done using virtual functions, while in Python it happens naturally through method overriding. So we define a base class named animal with the method speak. Then we create subclasses dog and cat, each overriding the speak method. Now when we loop through the list of animal objects, that is maybe dog, cat, animal, and call speak, each executes its own version. That is runtime polymorphism. The right method is chosen depending on the object's actual type. In Python, polymorphism doesn't need inheritance. This is called duck typing. Both duck and fish have a swim method even though they are unrelated. So Python says if it looks like a duck and swims like a duck, it is fine. When we call swim on each object, the correct method runs automatically. So for example, with super function, you can see that in dog class we can call the method of the parent class, that is animal's version of speak method, with super keyword or super function. So it first calls animal's speak version and then performs the logic that is written inside speak version of the dog class. So here we have three classes A, B and C forming a chain of inheritance. Each one defines a show method but calls its parent version with super function. When we call c.show, Python automatically resolves the order through method resolution order. So the output executes from top parent to the bottom child, that is A, then B, then C. To sum up, polymorphism let us write flexible and extensible code. Python's dynamic nature even supports polymorphism without inheritance. Meanwhile, super gives us a clean and reliable way to connect the inheritance chain. Now let's see abstract class and interface. Abstract class is like a partially built structure. You can't use it directly. It provides a foundation for other classes, ensuring that they follow a certain contract. In Python, we use built-in ABC module for this. We import ABC, an abstract method from ABC module. So animal inherits from ABC, making it abstract base class. The speak method is marked with the marker at abstract method, meaning subclasses must define it. You cannot create an instance of animal directly, so it's just a contract. Now we create two subclasses, dog and cat, both inherit from animal. Each provides its own definition of speak. Now we can create dog and cat objects and call speak polymorphically. If any subclass forgets to implement speak, Python raises an error enforcing design integrity. So in Python, interfaces don't exist as a separate keyword, but we can mimic them using abstract base classes with only abstract methods. So abstract classes can share logic, while interface-like classes only define rules. Here we define an interface like abstract class drawable. It only declares draw, no implementation. Every subclass like circle or square must define draw function. This ensures consistency across all drawable objects. Abstract classes can have both concrete and abstract methods. So vehicle defines a concrete start method and an abstract fuel_type function. Car inherits and implements only abstract part. This gives us flexibility, that is shared behavior plus some custom rules. In Python, aggregation and composition concepts mean exactly the same as in C++. They describe has a relationship between the objects. So in this example, let's quickly see how this is done in Python. Car has an engine showing composition. So the car owns its engine object, and when the car is destroyed, the engine goes with it. If we wanted aggregation instead, we will just pass the engine into the car's constructor rather than creating it inside. So the concept and purpose all remain identical to what you have already seen in C++. So nothing new here conceptually. So Python just makes it cleaner with dynamic typing and no need for pointers or explicit descriptors. So here's how OOP concepts map one-to-one across both the languages, that is classes, objects, inheritance, polymorphism exist in both. Only the syntax. So here's a quick comparison among the both implementations in C++ and Python. So with respect to class definition, they have a similar structure, but Python uses indentation instead of braces. For object creation, Python always uses parentheses in constructor call. Access specifier, Python relies on naming conventions. For constructors, in C++ you define class name methods, and in Python, as we have covered the initializer method, the init method. So Python uses magic methods for again operator overloading. So in C++ we have studied the concept of destructor. In Python, the garbage collector handles all the cleanup. The syntax is almost similar for inheritance. Python supports multiple inheritance more easily, and it is inherently polymorphic. You can do dynamic binding by default, but as you can recall that in C++ for achieving polymorphism you have to use virtual functions. So encapsulation is enforced with the help of access specifiers in C++, while this is achieved using naming conventions using Python. So again, conceptually same, but less strict in Python. Operator overloading, we have overloaded several operators in C++. So in Python, as we have just discussed, the idea is same, but the syntax is different. We use magic methods. For abstract classes, C++ implementation uses pure virtual functions, whereas Python implementation uses ABC module. So both of them enforce method implementation, and in C++ memory management has to be done manually. You manually allocate and deallocate the memory, whereas in Python this is done with automatic garbage collector. So Python basically simplifies resource handling. And this brings us to the end of this object-oriented programming journey from C++ to Python. So across both the languages, we have seen that while syntax may change, the core concepts remain exactly the same. Whether you are defining the classes in C++ or Python, what truly matters is your ability to think in objects, to design relationships, responsibilities, or behaviors that mirror the real-world system. Thanks for watching, and keep coding with clarity and creativity.